Lesson 3, Module 1, and it's only the first part. This is something to do after you've done the POGL on measurement and sig figs. So measurements, anytime you make a measurement, the instrument itself is never going to read infinite numbers of decimal places. So the instrument is always limited. So we're going to talk about first accuracy and precision. To be accurate is to be close to the actual value, what it should be. So if I calculate the density of something, let's say it's aluminum and it's 2.6, and that is, the true value is 2.6. So I would be very accurate. Precision is how close your measurements are to each other, how consistent you are. And this is also depending on the instrument that you use. So if you look at the analogy are these kind of bullseyes where the dart is going to be a measurement. And if you have more than one dart, that means that you're doing more than one trial. So just, assuming you're trying to hit the bullseye, if you throw it, you hit the middle is what you should have got, then you're accurate. Over here, you can see that this person's measurements are consistent. The darts are all in the same spot. So these would be precise, but not accurate because they're trying to hit the bullseye. If you're both, then you're consistent. Like if you do 3 trials, they're going to be very close in value, and they're also going to be close to what the true value, accepted value is. And then it's possible to be neither. This is just kind of random and not hitting the true value, so not accurate, and not being consistent, and so not precise. Error is what we call just the difference between the experimental value and the accepted value. So if I got a density of 2.7 and really the density is supposed to be 2.6, then my error is going to be 0.1. And we're just going to do absolute value for this, so just subtracting the difference and, how far off are you? We can also kind of look at, here is something where someone was calculating density, and you can see the accepted value is 1.59. So like the difference here between that and 1.54, which these are the experimental values, these are the errors. And they, in the book, this is from the textbook, they do positive and negative. We're just going to do absolute values so that they're always positive. So I'll keep going, I think. So percent error is just a way to take that error and put it into a percentage. So we do, again, this is different than the textbook. We do the absolute value of that difference between the accepted or the true theoretical value versus the true measurement, the experimental value, and then divided it by the accepted value again. And then we multiply by 100 to make it into a percentage. So significant figures from the POGL, hopefully you understood that. It's all the numbers that you're sure of plus one more that you estimate. The tricky part is when you're talking about zeros. When are they part of the measurement and when are they just placeholding? So for this example here, you can see that they're measuring the, so it's going to be 5.2, like we're sure of that. And then it's just a little bit further. So you could say, it's 5.21, 5.22 centimeters. And we're all correct. So we can differ in that last kind of guessing digit. So, here, we'll leave that. Let's just go. So here, if we're measuring volume, you can see that we're, every dash is a 1, so this will be 21, 22, 23, 24. So we're sure that it's past the 21, and then we can estimate one more. So if it's marked by the ones, then we can estimate to the tenths. If it's marked to the tenths, then we can estimate to the hundredths. So we can always go one more guessing digit past whatever the um, tool has its increments, I guess. So determining sig figs, the rules are on the POGL, very similar to these. So any number that's not a zero is automatically a significant figure. It was part of the measurement and the estimated digit. It's those zeros that are harder to deal with. So zeros that are, I call this the sandwich rule. So if you have like a 1, which you know is a significant figure, and then you have a 9, these are significant. So then the middle part has to also be significant. All final zeros to the right of the decimal are significant. So for example, 17.00, those two zeros are significant. And then we have rule 4 that placeholding zeros are not significant. So if I have 0.0015, these are not significant. I call those leading zeros, and they are just placeholding. Other placeholders, if you have the number 1500, these two zeros at the end are not significant. They're placeholding. Counting numbers and definite constants have infinite numbers of sig figs. So if I count like 15 cars, there's no doubt about that. There's 15 cars. Also, constants like pi, which keeps going on, have infinite sig figs. So an example, determining the sig figs in these numbers. So here, you can see that this 0 and this 0 are significant because they are following a decimal and a number. And then we know all of the non-zero numbers are significant. So we have 5 significant figures here. These first zeros are not significant because they are placeholders. Letter B, these 3 are significant. So there's 3 sig figs. The other 3 are not because there's no decimal present. It was a comma. I don't know if you saw that, but if it were a decimal, then everything would have been significant. This one, all 3 are significant. This 0 counts because it's after a decimal and a number. The 2 counts, so therefore the 0 in the middle counts. So this has 3 sig figs. This number also, sometimes in math, we know that the decimal is implied. In science, if you put the decimal on the end, then that makes kind of a sandwich again. So that makes all of these count. 100 only has 1 sig fig. How would we write it with 2? So if I want 100 to have 2 sig figs, I would be forced to write it in scientific notation. So now it has 2 sig figs. I could write it with 3 sig figs. I could also just do this, so now it has 3 sig figs. So on the POGL, just this last page, we're going to circle the zeros that are significant, and they're not just placeholding. So these are significant. So are these. These other zeros that you can see are not significant. They're placeholding. Over here, this one is significant. So that's just the zeros. Then we get down here and we can look at the numbers, and there's the rules are up above on the POGL. Here you have 2 significant figures. Here we have all 4. Here, when it's in scientific notation, all of the numbers are significant. Here's a counting, so this has infinite sig figs. This one, it's the first 4 that are significant. This one, all of them are. Then over here, we've got these four. So notice those leading zeros that start are not significant. Those are placeholding. These are all significant. This is the definition, so really infinite sig